Continuing our discussion of Lewis structures, I want to go over a couple of examples where our Lewis structures will have double and triple bonds, and also I'll state very clearly the step-by-step instructions that most people use to draw valid Lewis structures. The examples that we're going to be looking at are shown here. Draw valid Lewis structures for the following and your given chemical formulas. Before we take a look at the rules or the guidelines to draw Lewis structures for these compounds, I just want to remind you that in the introduction to Lewis structures in video 06A50, we went over some very basic bonding rules for neutral atoms. Do you remember this table here where we look at carbon, nitrogen, oxygen, fluorine, and hydrogen, and we were able to figure out how many bonds each of those atoms have and how many lone pairs each of those atoms have when they are in compounds. And the example compounds are here on the right. But let me go over some formal rules. Maybe this will help the rest of you who weren't able to really catch on to that bonding table. So I have these written out already. Please pause the video if you want to copy these. These are going to be steps to draw Lewis structures. And for now, we are going to practice with neutral compounds, not polyatomic ions. So we are going to be using these rules because these were the rules for neutral carbon, nitrogen, oxygen, fluorine, and hydrogen. Okay, first rule. Let's call these guidelines actually, or steps. Based on the chemical formula, determine the number of valence electrons. So for each of these examples, we are going to determine the number of valence electrons based on each atom. For instance, carbon has 4 valence electrons, hydrogen 1, and etc. Okay. You don't need to know the structure before you figure out the number of valence electrons. That's just coming from the periodic table or your electron configurations for each atom. So you'll have a number. Go ahead and jot that down as the number of valence electrons. And now, since we're putting together these atoms in some order, for most cases, I'm going to say the central atom is obvious. Sometimes it's not obvious and you'll be given a clue. Don't worry, we'll look at some examples in just a bit. Oh, I have some other hints about the central atom. First of all, hydrogen and halogens. Okay, those only have one bond when they're neutral, so they cannot be central atoms. Central atoms are the atoms in the middle that have several single, double, or triple bonds around them to the neighboring atoms. Once you think you have the central atom, you're going to draw that central atom, and then you're going to draw single bonds from that central atom to the outer atoms. Okay. Rule or guideline 3 is a little bit long. Let me show you all of it. Because each of those single bonds represents 2 valence electrons. So we have a total in our heads, and we subtract the number of electrons we have that are in bonds, number of valence electrons that we have in bonds. And then we're going to place the other valence electrons as non-bonding electrons on the appropriate atoms, based on the number of valence electrons they brought. So for instance, if I have an oxygen, it has 6 valence electrons. If one of those electrons is part of a covalent bond, right, because it's contributing to that bond, then we have what? 6. We have 5 other non-bonding valence electrons that we have to take care of. And we're going to put those 5 dots around the oxygen, because one of those dots, the 6th dot, the 6th valence electron, was used to make a bond. Right now it's a little bit abstract. this will become very clear once we start practicing. And so while this is a pretty convoluted rule, we will practice, all right? So don't worry. We have 6 examples to get through. Number 4, and it's the last guideline. Check if all non-hydrogens satisfy the octet rule. If not, move the non-bonding electrons to the adjacent bonds to get atoms to satisfy the octet rule. Now, some of this will be trial and error, because we're going to be shifting electrons, and we're going to try to figure out a way. It's like a puzzle. We're going to try to figure out a way to shift those electrons into bonds so that every non-hydrogen atom satisfies the octet rule. And so for some people, including myself, this will be trial and error. If it doesn't work, then start over and start shifting other electrons. The other note before we get to those 6 examples is that later on, not in this video, we will see exceptions to the octet rule. So later on, we will see exceptions to octet rule. Okay, let us grab a new piece of paper and start trying these examples. The first example is CHCl3. Again, I would suggest jotting down those rules, and we're going to refer to them as we go through each of these chemical formulas. A, CHCl3. I'm just looking for my periodic table. Okay, first step, based on the chemical formula, determine the number of valence electrons. Carbon has 4, so this should be pretty automatic by now. Carbon has 4, hydrogen has 1, and then we have 3 chlorines. Chlorines are in the halogen group underneath fluorine. So fluorine has 7 valence electrons, chlorine 7, bromine 7, iodine 7. The halogens have 7 valence electrons. So 3 times 7 equals, what is this, 21, 22, 26. Okay, good. Because in the previous video, when we introduced Lewis structures, all those compounds had 8 valence electrons. So I want to look at some variety. 26. Next step. For most cases, the central atom is obvious. H and halogens only have 1 bond when neutral, so they cannot be the central atom. We have an H and we have 3 halogens. They are not the central atom, so carbon is the central atom. Okay, so that's what I mean by most cases it's going to be pretty obvious. This green bullet point here, draw single bonds from the central atom to the outer atoms. So the outer atoms are going to be these 4. It doesn't matter where you put the H and the Cl's around the carbon, as long as they're all singly bonded to the carbon. Okay. Now, it says here, for number 3, each single bond represents 2 valence electrons, 1 from each atom usually. So place the other valence electrons as non-bonding electrons around the appropriate atoms based on the number of valence electrons they brought. We started out with 26, and then each of these are 2 valence electrons. So we now have 26 minus 8, 2, 4, 6, 8. And what is that? That equals 18. That seems like a lot. So we have 18 electrons to take care of, 18 valence electrons. It's a lot, but remember how we said chlorine has 7 valence electrons? I mean, we could put it off to the side. Chlorine comes to the bonding party like this. So this unpaired electron not probably, will say that it's helping to make the bond. The other electron of the bond is coming from carbon. So we took care of only one of the 7 valence electrons for each chlorine. Chlorine has another 6. That's what I mean by putting the other electrons around the appropriate atoms, because each of these chlorines came with 7 valence electrons to the bonding party. Okay. So think about that. Um, think about how many valence electrons each atom 26, the magic number. 1, 2, 3, 4, 5, 6, 7, 8. And then each of these chlorines has 3 lone pairs, which is a total of 6 non-bonding electrons for each chlorine. So 6, 12, 18 plus 8. So that's 26. Check. That's the Lewis structure for CHCl3. What rule didn't we use? Oh, actually we will use it, but you'll notice that we won't have to do anything. It's check if all non-hydrogens satisfy the octet rule. The carbon satisfies the octet rule. This is another skill that we talked about on the previous video. How do you count which electrons are applied to the octet rule? You count every electron that is around that atom. So for the carbon, this is how you would count. 1, 2, 3, 4, 5, 6, 7, 8. You count both electrons of the bond, even though carbon only brought 4 electrons. 1 electron per bond. So you count all the electrons. So carbon satisfies the octet rule. Look at this chlorine up here. We are still counting both electrons of this bond, even though we counted it for this carbon. So for chlorine, it's 1, 2, 3, 4, 5, 6, 7, 8. So chlorine satisfies the octet rule. That's the beauty of covalent bonding. Because you are sharing those electrons of the bond, you use those electrons in figuring out whether each of these atoms satisfies the octet rule. And they all satisfy the octet rule. Okay. Hydrogen, except for hydrogen. Hydrogen only has 2 valence electrons. So we can say chlorine, we should say carbon, but chlorine, 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 and carbon all satisfy the octet rule. Okay, let's take a look at the next example. Let me focus this a little bit better though. I can. Uh-oh. This is not manual focus. Hopefully this works. In the meantime, for B, it's CS2. Okay, for CS2, it's not unambiguous what's the central atom. So let me put another tip here. Usually, the central atom is the least. It's called electronegative. The least electronegative atom. What's electronegative? So at this point, we haven't talked about electronegativity. It's the propensity of an atom to become negative, to make an anion, or to gain an electron. How about that? So the more electronegative an atom is, the more likely it is to become an anion. It actually follows the same trend as electron affinity. So we do know electron affinity. The higher electron affinity, the more electronegative. Just remember, fluorine had the highest fluorine had the highest electron affinity when we talked about those trends. So fluorine is also the most electronegative atom. It wants to be F minus. Okay, regardless of, we're not talking about whether it's in a compound or not. Just by itself, that atom wants to be F minus. It wants to gain an electron to get to the noble gas configuration of 8 valence electrons. So just remember that F is the most electronegative atom. I know that's a lot just for this compound here. What this means is that carbon is a central atom. Now, sulfur is right underneath oxygen. Fluorine is the most electronegative atom. Second actually is oxygen. And sulfur is, since it has the same bonding trends as oxygen because it's in the same column, same group, sulfur you will assume that it has a higher electronegativity than carbon. And we said here the central atom is usually the least electronegative. So sulfur is more electronegative, carbon is least. Oh, before we start drawing anything, how many valence electrons does this have? Carbon has 4. There are 2 sulfurs, and they're like oxygen, they each bring 6. 12, 13, 14, 15, 16. All right, 16 electrons, valence electrons. Okay, we have the central atom. You're going to make single bonds to each sulfur. Okay. We have how many electrons to take care of? We have 16. We've already taken care of 4. 2, 4. So there are 12 available. 12 as non-bonding for now. Okay. The other way we could think about it is carbon brought 4 valence electrons with it. We used 1, 2, and I'm going to put them like this, 3 and 4. Sulfur brought 6 valence electrons. 1, 2, 3, 4, 5, 6. Okay. Don't worry right now that some of these electrons are unpaired. Right now we have to figure out where are those 16 valence electrons. 1, 2, 3, 4, 5, and then the 6th one from sulfur is making this bond. So this is where we are going to use step number 4. Check if all non-hydrogen atoms satisfy the octet rule. If not, we are going to move non-bonding electrons to the adjacent bonds to get atoms to satisfy the octet rule. Because right now, carbon doesn't satisfy the octet rule. It has 1, 2, 3, 4, 5, 6 atoms, 6 electrons around it. Sulfur, 1, 2, 3, 4, 5, 6, 7. Ugh. So none of these atoms satisfy the octet rule. This is where I mentioned that this step may be trial and error, but we're going to start moving electrons to try to get each of these atoms to satisfy the octet rule. Now, that's why I want us to learn also the bonding table, because we know that carbon in the neutral state wants to have 4 bonds. Oxygen wants to have 2 bonds, right? That's why I went over this in the introduction. the first thing we learned were these bonding rules. Why did I say oxygen? Because sulfur is in the same group as oxygen. So knowing that, this is how I'm going to move the electrons. I need carbon to have 2 more covalent bonds. So this is our first example where we're going to have double bonds, and I'm going to bring this electron down, and for sulfur, I'm going to bring this electron to the bond as well. You see what that accomplishes? We're going to redraw this now, and those 2 electrons that I just moved with the pink arrows make a second bond. That is called a double bond. But look at sulfur. We went from 1, 2, 3, 4, 5, 6, 7, right? When we're figuring out the octet rule, to now 8. 1, 2, 3, 4, 5, 6, 7, 8. So sulfur is good. Sulfur satisfies the octet rule. Why don't we do the same thing on the other side? Move this. Move this unpaired electron to start making a bond with this unpaired electron as well. Remember, 2 electrons makes a bond, but now we have a double bond. Okay. I do expect scratch work when my students take the exam. They know that they have to circle their answer so I could find it. That is the valid Lewis structure for CS2, and we could double check. Carbon now. See, it went from 1, 2, 3, 4, 5, 6 electrons for the octet rule to the proper 1, 2, 3, 4, 5, 6, 7, 8. S, C, and S all satisfy octet rule. Do you see how important the octet rule is? It's going to cause us to shift electrons to make sure that all the non-hydrogen atoms satisfy it. Now again, in not the next video, but in a future video, we will see exceptions, but not for any of these cases over here. Okay. All right. HCN. And there was a clue that the C is the central atom. C is the central atom. All right. Hydrogen has 1 valence electron, carbon has 4, nitrogen has 5, we have 10. I wanted to give the clue that carbon is a central atom because nitrogen, let me think. There is no valid Lewis structure when nitrogen is a central atom in this case. So you put the central atom and you put the outer atoms bonded to it with single bonds. Hydrogen came with its 1 electron, so it's there. Carbon came with 4. 1, 2, 3, 4. Nitrogen came with 5. 1 made the single bond. 2, 3, 4, 5. Okay. At this point, it doesn't matter whether you draw these as pairs or single electrons. But we do notice that carbon doesn't have 4 bonds. Carbon doesn't satisfy the octet rule. We're not going to make a double bond to the left because hydrogen only wants 1 bond. We're going to put both of these unpaired electrons here. Oh, actually, let me do it one at a time. Just to show that I do trial and error as well. It's just that I was very familiar with this molecule, so I know what the final answer is. Well, we need another electron to make a bond, so we're going to move this electron here as well. If I redraw what my pink arrows are telling me to do, I have this situation. I only moved 1 electron from the top of nitrogen. I still have 10 valence electrons. Here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And over here, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, here it is, 10. See, I didn't move this electron on the bottom. Okay. Still, carbon doesn't satisfy the octet rule. 1, 2, 3, 4, 5, 6, 7. Nitrogen doesn't satisfy. 1, 2, 3, 4, 5, 6, 7. We also know from our bonding rules that nitrogen in the neutral state has 3 bonds, just like this example here. Right now it only has 2. Let's keep moving electrons and redraw our result. Carbon, 1, 2, 3, 4, 5, 6, 7, 8. Check. Nitrogen, 1, 2, 3, 4, 5, 6, 7, 8. They both satisfy the octet rule. The compound has 10 valence electrons. At the very end, that's what you're checking. Make sure that you didn't lose electrons, valence electrons, and make sure that every non-hydrogen atom satisfies the octet rule. Next example. Oh, before we get to the next example, let me just point out, just like my title said, we will be looking at molecules that have double bonds. So this is a double bond. And now we have an example of a molecule with a triple bond. If you're very good at counting, you know that this triple bond is represented by 6 valence electrons, 2 for each line. The double bond is represented by 4 valence electrons, 2 for each line as well. Okay. Yep, this video is running a little bit long, but I am going to get through these examples. Actually, how about this? Those are the last 3 examples. Why don't you pause the video and try your best to answer the valid Lewis structures for each of these. When you unpause it, I'll show you how I would do it, but it's going to be quick, okay? The way I do it. Okay. All right, for NF3, five plus 3 times 7 equals 21. 6. N is the central atom. "26 electrons total, and the F, 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 and the N all satisfy the octet rule. Even nitrogen, 1, 2, 3, 4, 5, 6, 7, 8. Here we didn't have to shift any electrons, so we don't have any double bonds or triple bonds. After we put the central atom, the single bonds, and all the other valence electrons, we were good. There was no need to shift electrons because all of them fits the octet rule. The next one. This one's a little bit trickier. We have 2 atoms that are not hydrogen. Those 2 atoms have to be, you could even think of it as the co-central atoms. There's no way that hydrogen can be a central atom. So we know for a fact that that carbon and nitrogen have to be connected to each other. They have to be connected to each other. The way that they wrote the chemical formula implies that these 3 hydrogens are around carbon. So we are getting some structural information just by the way they draw the chemical formula. It's not actually a chemical formula, it's a chemical structure because they're implying that these 3 hydrogens are around carbon, these 2 hydrogens are around nitrogen. So it gives you structural information, not just the number of atoms of each element. Nitrogen brought 5 electrons to the bonding party. 1, 2, 3. Oh, there it is, 4, 5. Okay. So I did this without having to really count the number of valence electrons because I knew where the connections of the atoms, but I also knew carbon wants to have 4 bonds, nitrogen wants to have 3 bonds and 1 lone pair. But we could double check. 4 plus 3 times 1 for the 3 hydrogens, plus 5 for the nitrogen, plus 2 times 1. What is that? 3, 7, 12, 12, 15? Is that right? That can't be right. 3 plus 4 is 7, plus 5 is 12. Oh, 13, 14. Oh my goodness, my math. 2, 4, 6, 8, 10, 12, 13, 14. So that's good. Carbon and nitrogen both satisfy the octet rule. Okay, last one. F. This one's weird. CH2O. Like I said, hydrogen can't be the central atom. Let's start somewhere. We have C and we have O. So the tricky part is where are those hydrogens? Because the hydrogens again are next to the carbon, let me try on first pass to put the hydrogens off of the carbon. Okay. Now let's fill in the valence electrons. And in this case, I will count to help me figure out the structure. 4, 2 times 1, oxygen has 6. That's 12. 1, 2, 3, 4, 5, 6. So I need 6 more. You know that oxygen came with 6 valence electrons. So there's 1 there, 2, 3, 4, 5, and 6. Where's that last electron? Because right now I only have 2, 4, 6, 8, 10, 11. Remember that carbon had 4 valence electrons brought to the bonding party. 1, 2, 3, 4. You notice that carbon does not satisfy the octet rule. 1, 2, 3, 4, 5, 6, 7. Oxygen, before we move this electron, doesn't satisfy the octet rule. 1, 2, 3, 4, 5, 6, 7. Again, trial and error. You know that a bond needs 2 electrons, so I am going to move both of those single electrons to make another bond, so it's doubly bonded. I have 2 lone pairs left over. Nothing happened to those. And now double check. First, let's check that there are 12 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Check. Make sure that carbon and oxygen satisfy the octet rule. 1, 2, 3, 4, 5, 6, 7, 8. For oxygen, 1, 2, 3, 4, 5, 6, 7, 8. There's plenty of practice in your textbook. We just did 6 together. The last 3 a little bit faster. In the next video, we are going to look at now molecules that have charges. So the complexity is getting a little bit harder. Remember, for these steps, we were mostly concerned about neutral compounds. In the next video, we're going to look at polyatomic ions, the Lewis structures of polyatomic ions.